Welcome back to the Deep Dive. Today we are taking a look at the entire blueprint of artificial intelligence. You know, the LLMs, the massive image generators, the agents that are, well, starting to run a lot of our lives, and we're looking right past them. Because the dominant paradigm, the thing we call AI right now, is on the verge of a really fundamental transformation.
It absolutely is. And that transformation, it's not just for fun, it's necessary. Because for the last decade, AI has really been defined by the success of just brute force pattern matching. Think about it. Large language models, model-free reinforcement learning agents, they're all what the Nobel laureate Daniel Kahneman would call System 1 thinkers.
Right, the fast, intuitive gut reaction system.
Exactly. They're incredibly fast, they're intuitive, and they rely completely on statistical correlations they've learned from just oceans of data. They map an input to an output, and they're brilliant at it. They're amazing statistical machines. But they fundamentally lack an internal model of causality or, physics.
So they don't actually know why a glass shatters when you throw a ball at it.
Not at all.
They just know that in the training data, when a small, fast object gets close to a transparent, brittle object, the next sequence of pixels usually involves a bunch of shattered fragments. They're just correlation engines.
That is the crucial distinction. You've hit it right on the head. They are not simulators. They operate based on association, not deep, predictive understanding. And that gap, that inability to reason about physics and causal rules, that's precisely what we're going to bridge in this deep dive. We're moving into the era of world models. And this represents a fundamental phase transition in how we build AI.
Okay, so let's unpack that definition, because world model sounds almost philosophical, but it has very concrete engineering implications.
Yeah.
In technical terms, what exactly is a world model? What job is it doing?
At its core, it's a compressed, actionable simulation of the environment. And the key part is that it's learned entirely from data, from the agent's own experience. Think of it as an internal, self-constructed game engine.
A game engine, it built itself.
Exactly. And its whole purpose is to allow an agent to imagine the consequences of its actions before it actually takes them in the real world. Wow. So the whole strategy shifts from, trial and error out in the real world.
Which is expensive.
Incredibly expensive. And it shifts to simulation and planning entirely inside this compressed latent space.
And that immediately solves that huge cost problem from early AI, right? Where a model-free agent needed, millions of frames of real-world data just to learn how to open a door in a game. It learned by failing over and over.
And this transition, this power of imagination, it's all driven by this one central hypothesis in the field, which is that prediction is the essence of intelligence. If a system can accurately predict the future state of its environment, given its current state and some action it's thinking about taking, it has implicitly learned the environment's causal rules. You just can't predict the future of a system without understanding its physics. So our mission today is to trace this architectural journey, starting right at the foundation back in 2018, and see how we engineered our way to AI systems that can, literally dream the future.
Okay, let's set the historical scene for everyone. Before 2018, if you were building an agent to play, say, an Atari game, you were probably using a model-free technique, something like DQN. And that would directly map raw pixels from the screen to actions on the controller using a big convolutional neural network. You said these were notoriously brittle and sample inefficient. How inefficient are we talking about here?
We're talking about training that often stretched into hundreds of millions of steps in the game, millions and millions of frames.
Yeah.
And brittle meant that any tiny change, like if you just change the background color of the game, could cause the agent to completely fail.
Because it wasn't understanding the game, it was just memorizing pixel patterns.
It was just mapping visual correlations, exactly.
Yeah.
So that was the baseline, and it demanded massive compute and a lot of time.
Then in 2018, this seminal paper comes out by David Ha and Jürgen Schmidhuber. It was just called World Models. What was so radical about their architectural proposal?
It was radical because of its commitment to modularity. They basically argued, let's stop trying to do everything end-to-end in one giant monolithic network. Instead, let's separate the concerns into 3 independent specialized models: Vision V, Memory M, and Controller C.
Perception, prediction, and control, all decoupled. That feels a lot more like good software design, honestly.
It is. It's much more robust.
Okay, so let's start with V, the vision model. The first huge hurdle you mentioned was the curse of dimensionality. How big of a problem is that for a machine trying to learn?
It's computationally paralyzing. I mean, just think about a standard small video game frame. Can be 64 by 64 pixels with 3 color channels, red, green, blue. That single snapshot has over 12,000 unique data dimensions.
12,000 numbers for one frame.
And feeding that raw 12,000 dimensional stream into a memory model, every single frame, it just makes the whole system intractable and incredibly slow. So the V model's one essential job is just aggressive spatial compression, turning that huge observation into a tiny, compact, latent vector. We call it VNL.
And the tool they picked for this was the variational autoencoder, or VAE. This is a pretty common concept in AI now, but how did they use it here to create a latent space that was actionable, not just something that could create a pretty picture?
Right, and this is where the VAE's objective function, the evidence lower bound, the ELBO loss, becomes the core engineering insight. This loss function forces the system to balance two competing priorities. The first part is simple. It's the reconstruction loss. It just forces the output image, the one you rebuild from the latent vector, to look as close as possible to the original input image.
That makes sense. If I squish this image down to, say, 64 numbers, I have to still be able to unsquish it and recognize the car in the road.
Precisely. But the second term, that's the crucial constraint. It's the KL divergence loss. And this term, it acts like a regularization leash. It forces the distribution of those little latent codes, the zero-dotting vectors, to stick very closely to a simple, predefined probability distribution, usually a standard Gaussian.
Wait, hold on. Why would you force it to conform to a simple Gaussian? Isn't that like putting an artificial restriction on what it can learn?
It absolutely is, and that's the strategy. By imposing this strict rule, the VAE is fundamentally forced to learn a highly efficient, what we call disentangled representation. It can't afford to waste its limited latent budget on memorizing high-frequency noise, the visual static on the screen or the exact texture of the asphalt. It has to filter out the junk and only keep the few most important task-critical features. Things like the position and velocity of the car, the things it absolutely needs for a perfect reconstruction. If the model gets lazy, the KL loss penalizes it. It forces simplicity and generalization.
So V handles the efficient encoding of space. Now we move to M, the memory model, which has to handle the progression of time. If V gives us a compressed state, ZOT, then M needs to predict the next state, ZOT plus $1, and more than that, the whole future sequence of states.
Right, and M is a recurrent neural network, an RNN, specifically an LSTM or a GRU, and it operates entirely on these compressed latent vectors. But the researchers immediately ran into a classic problem with prediction, which is stochasticity. The real world is uncertain. The future is multimodal.
Give me a concrete example of what that challenge looks like.
Okay, imagine the agent is driving in a racing game. It comes up to a sharp curve. It could either brake hard and turn less, or it could maybe ease off the gas and turn right. There are multiple valid futures. Now, if the agent proposes an action like turn the wheel a little bit, the immediate next state is inherently ambiguous. If they used a standard mean squared error loss, which is designed to average things, what state would it predict?
It would predict the average of those two distinct possibilities. So in your example, it would predict the car driving straight into the median, right between the two valid paths, which is an impossible physical state.
Exactly. A prediction that is physically impossible is useless for planning. So the brilliant solution here was to introduce a mixture density network, an MDN, as the output head of the RNN. Instead of predicting one single future vector, the MDN outputs the complex parameters, the means, the variances, and crucially, the mixing coefficients for multiple Gaussian distributions.
So this lets the model say, okay, the future is definitely going to be one of three things. There's an 80% chance of option A, a 20% chance of option B, and a 0% chance of option C.
That's the strategic insight. It lets the model assign high probability to distinct separate outcomes. High probability for the car making the turn and staying on the track, and 0 probability for driving into the wall. It captures the true uncertainty and the branching paths you need for complex long-term planning.
Okay, so V compresses the scene, M learns the physics and the time dynamics. That brings us to C, the controller model. And since V and M are doing all the heavy cognitive lifting, all the perception and the dreaming C gets to be surprisingly simple.
It is the ultimate testament to how well V and M work. The controller is often just a single-layer linear perceptron, a really simple network. It just takes the current visual latent vector, Z in dollars, and the memory's hidden state, HT dollars, and outputs the best action, HT. And because the controller had so few parameters to train, the researchers didn't even use standard gradient descent.
Right. They used the covariance matrix adaptation evolution strategy, CMAES. That's a gradient-free evolutionary method.
It is. And by using CMAES, they avoided this huge computational headache of backpropagating gradients through time across the entire recurrent memory model. It made training much, much faster and simpler. And this separation of training, it allowed for this breakthrough concept, what they called training in the dream.
That phrase sounds like it's straight out of a sci-fi movie. What did that actually mean in practice for the agent?
It meant that once the memory model, M, was trained and stable, you could basically disconnect the agent from the real environment. The M model became a self-contained simulator. It was running its own little latent physics engine based on what it had learned. The agent could then train its controller, C, entirely inside this hallucinated virtual world.
Wait, so they trained the agent in a hallucination, and it performed better in the real simulator than policies trained directly on the real data. That is genuinely counterintuitive. It's a massive validation of the model's internal understanding.
It was proof that the model had captured the underlying physics, not just the pixels on the screen. And they showed this so clearly with the Kerosene V0 task. Agents trained only inside the model's dream performed at a state-of-the-art level in the actual external simulator. The model wasn't just generating cool video, it was generating an actionable world model that was good enough for planning.
But like all foundational research, it had its limits, and those limitations are what drove the next generation of work. You mentioned 3 key problems.
Right. The first, and probably the most important for actually winning the game, was the VSE bottleneck. Since the vision model, V, was only trained on pixel reconstruction, it only cared about visual fidelity. This often meant it would prioritize visually dominant but, task-irrelevant features, like the big blue sky in the background of a game, instead of the tiny but critical enemy bullet coming from the corner. We call this loss misalignment.
So it's focusing on making the sky look perfectly blue to satisfy the reconstruction loss instead of noticing the 1 pixel that means life or death.
Precisely. The second issue was hallucination drift. While the predictions were great in the short term, over long prediction horizons, the errors would accumulate. The RNN's predictions would gradually drift away from realistic physics into these impossible, weird states. And finally, the separate training. V, M, and C were trained sequentially. This made it impossible for the controller to feedback and influence how the vision system decided to compress the world. That lack of end-to-end optimization is what DeepMind set out to fix with the Dreamer lineage.
And that brings us to 2019 and the work from Google DeepMind, the Dreamer series V1, V2, V3. This whole lineage feels like the stabilization and maybe the industrialization of the world model concept. It unified that modular VMC architecture we just talked about under one name, the Recurrent State-Space Model, or RSSM.
That's a great way to put it. It was about taking this brilliant idea of VMC and making it robust, making it scalable. Dreamer V1, which came out in 2019, focused immediately on solving that optimization problem by introducing what they called differentiable planning.
Okay, hold on. If you make the entire world model differentiable, meaning you can pass gradients all the way through your dream simulator and back to the controller, isn't there a huge risk? Like, the planning could run away, get stuck in local optima, or just be way too slow compared to the gradient-free CMAES.
That was the engineering trade-off, for sure. But the benefit of using analytic gradients, it just outweighed the risks. Because the world model and the value function, the critic, were now differentiable, the agent could literally propagate its desire for high rewards backward through time. And not just one step, but across an imagined trajectory of dozens of future steps. It imagines a path to a high reward, calculates the gradient of that entire path, and then adjusts its actions. It's just immensely more sample efficient than trial and error.
I see. It's giving the agent foresight. It's not just reacting. It's actively maximizing future value based on its internal dream. And the RSSM architecture was the key to managing the stability you'd need for that kind of deep backpropagation.
Yes. The RSSM structure, which is still central to this whole lineage, it manages that complexity by splitting the state into 2 vital components. First, you have the deterministic state, which is usually modeled by a GRU. This handles long-term memory and context, things that are certain, like, I have already picked up the key, the door is now open.
The facts of the world.
The facts. And second, you have the stochastic state, which is the VAE-like component. This accounts for momentary uncertainty, the branching possibilities. If I run now, the enemy might turn left or they might turn right. And this split provides the stability you need. The deterministic state anchors the context and stops the stochastic part from drifting too far into that hallucination drift we talked about.
So that makes Dreamer v1 robust, but Dreamer v2 in 2020, that seems like the real watershed moment, because that's when model-based RL finally pulled ahead of the big model free agents. And the crucial insight was so counterintuitive, moving from continuous latents to discrete ones.
It was a massive conceptual leap. The core insight of Dreamer v2 was that the latent world, the internal representation of reality, should be categorical. It should be discrete, not continuous. They forced it into a grid of tokens.
But why would you abandon the mathematical richness of continuous variables, of Gaussians?
Because of a problem we mentioned earlier, which was now getting worse with scale. Posterior collapse. Continuous VAEs, when you optimize them just on the loss function, often find it's computationally cheapest to just ignore the input data entirely.
Oh,
They
right.
realize they can minimize the KL loss by just outputting the easiest possible thing, which is the average standard Gaussian distribution, no matter how complex the input image is.
So the model gets lazy. It decides, why bother encoding useful information when the penalty for being a non-standard is higher than the benefit of being accurate?
Precisely. And the result is an information-poor latent space. But also, think about it. The real world often functions categorically. An item in a game is either in your inventory or it's not. A switch is either on or off. When you try to average a continuous state between on and off, you just get a meaningless value of 0.5.
By forcing the latent state into a grid of discrete tokens, say a 32 by 32 grid of possible choices, you force the model to make hard, discrete decisions about the state of the world. You prevent that blurring effect.
That clarity is what forces the causal understanding you need for, Boolean logic. However, there's a mathematical problem. Sampling discrete tokens is non-differentiable. You can't backpropagate through a hard if-then choice. To get around this, they used a very clever trick called straight-through gradients. It basically bypasses the non-differentiable step on the forward pass, and then on the backward pass, it pretended the operation was continuous, allowing you to optimize the whole thing end-to-end.
That's the engineering hack that made the whole theory of discrete states actually work in practice. Okay, so that brings us to Dreamer v3 in 2023. This sounds less like a revolution and more like making the system robust enough for prime time.
Dreamer v3 is the industrial strength algorithm. Its main contribution was a really robust, universal training recipe that works across almost every domain you can think of. Atari, Minecraft, complex continuous control, without all the painstaking task-specific hyperparameter tuning that usually plagues RL research. And this out-of-the-box robustness comes from two critical technical innovations that deal with stability when you have massive variance in your data.
Okay, let's start with the first one, SimLog predictions. Why do rewards that range from, say, 1 to 1,000,000 cause a network to fail?
Well, deep learning networks work best when their targets are standardized, when they're in a manageable range, like between 0 and 1 or max 1 and 1. When the size of the rewards varies wildly, like a minor score update is 1 point, but finding a hidden treasure is 10,000 points, the network gradients that reflect those outcomes become unstable. The gradient for the tiny reward just vanishes. The gradient for the huge reward explodes. The network just chokes.
So how does the symmetric logarithmic transformation, SimLog, fix that instability?
It's just a really elegant mathematical solution. SimLog applies a logarithmic compression to those values, squishing them into a stable range. But crucially, it does this while preserving the sign, whether it's positive or negative, and maintaining high resolution near zero. It's like trying to measure both tectonic plate shifts and microvibrations with the same instrument. SimLog compresses the scale so the network can process both accurately and stably without the huge numbers dominating or the tiny numbers just disappearing.
Stable gradients, stable learning, got it. What was the second key innovation that stopped the model from getting lazy again?
It addressed the risk of posterior collapse one last time, but with a loss management trick: KL balancing and free bets. So we said the KL loss forces the latents toward a simple distribution. If the model gets too good at minimizing this loss, if it drives it all the way to zero, that means the encoder isn't encoding any information at all. You get collapse.
So free bits are a way to stop the model from winning the KL game too easily.
Exactly. They clamp the loss so it can never drop below a minimum threshold, usually 1 nat. This introduces a minimum information budget. You're just basically telling the model, you have to use at least this much of your latent capacity to describe the world, no matter how simple it is. You must encode something.
Yeah.
And this compelled the V3 model to always encode useful details for prediction.
And the ultimate achievement for Dreamer v3, the thing that proved it could do complex long-horizon planning, was that it was the first algorithm to successfully collect diamonds in Minecraft from scratch. No human data. That task requires not just movement, but complex tool crafting, resource management, deep exploration planning.
That's the proof in the pudding. It shows that this stable RSSM architecture can achieve true causal predictive intelligence. It can plan out sequences that require hundreds of steps, all in its latent dream space, making it an incredibly powerful foundation for autonomous agents.
Okay, so we've seen the Dreamer lineage perfect this model-based RL approach by focusing on predicting a compressed or abstracted version of the next state. But this focus on prediction seems to have triggered a serious architectural and even philosophical debate about what an AI should be predicting. And this debate was really crystallized by Yann LeCun at Meta.
Yeah, LeCun argued that the whole dreamer or generative approach, even with all its success, is fundamentally inefficient. It's flawed in its premise. The generative models we've been discussing are still trying to reconstruct every single pixel or every token in the environment.
You mean the exact texture of a brick wall, the individual raindrops on the screen, the rustling of every single leaf on a tree?
Exactly. And LeCun's critique was, why are we wasting massive computational power predicting all of this high-frequency, chaotic, and frankly, irrelevant noise when the agent's task is simple? The task is avoid the obstacle or find the goal. The model doesn't need to know the pattern of rust on a railing. It just needs to know the semantic state, is the rail there, and where is it going?
So his manifesto was clear. Instead of predicting the massive high-dimensional pixel data, which we can call $6, the model should only predict abstract representations, which we can call $6. The model needs semantic state, not visual texture.
And this philosophy led to the Joint Embedding Predictive Architecture, or JEPA, which Meta has implemented in their image model, iJEPA, and their video model, vJEPA.
So how does JEPA actually implement this representation-only approach? It sounds like a complex masking game.
It's actually really elegant in its simplicity. The architecture uses a context encoder and a target encoder. The context encoder takes the part of the data you can see, say, the first half of a video frame, and maps it to a latent vector, 6 monos. Then the target encoder, which is usually a stabilized, older version of the context encoder, it maps the hidden or future part of the video, the part you want to predict, to its representation.
And the predictor tries to guess sex molars based on the input 6 molars. So what's the key technical difference in the loss function here?
The absolute key is that the loss function never measures the difference between the prediction and the original pixels of the target. It only minimizes the distance between the predicted representation and the actual target representation, all within the latent embedding space. And this has profound implications for speed and robustness.
Right, speed and efficiency for one, since you're working in a much lower dimensional space.
Absolutely. VGPay trains significantly faster. But the crucial advantage for planning is its inherent invariance to high-frequency noise. If those irrelevant leaves are rustling randomly in the original video, the context encoder learns to just ignore that noise, because it's only penalized for failing to predict the semantic meaning of the target area. GP just naturally focuses on structural information like object shape and position, which makes it highly robust for planning where semantic state is everything.
So on one side, we have Meta arguing that prediction complexity is wasteful. On the other side, we have OpenAI and the scaling hypothesis, betting that brute force prediction forces physical understanding. And this brings us to the generative turn, dominated by these massive video simulators.
Right. The generative school of thought argues that if a model can generate video that is photorealistic and temporally consistent, it must have, implicitly learned the underlying physics. And the ultimate verification of this hypothesis is OpenAI Sora, which came out in 2024. This is the brute force scaling approach applied directly to the world model problem.
Let's dive into the Sora architecture. It couldn't just process raw video, right? Because of the massive variance in aspect ratios and resolutions from its internet training data.
That's right. The core innovation wasn't really the diffusion process itself, it was the data preprocessing. They use a massive VAE to first compress the raw video into a dense 3D latent volume encoding height, width, and time together. This compressed volume is then adaptively chunked into uniform little blocks called space-time patches.
And these are basically the video equivalent of the standard tokens that LLMs use.
Exactly. By treating video as a sequence of these 3D tokens, Sora could train on videos of any length, resolution, or aspect ratio, which enabled just unprecedented data scaling. The core mechanism is a diffusion transformer, a DIT, that takes noisy patches and predicts clean, coherent patches, generating the next frame or the next sequence.
And the claim is that complex simulation capabilities, like 3D consistency, object permanence, simple physics, they just emerge spontaneously as you scale the model and the data.
The emergent is striking. It is. The model really seems to know that if an object goes behind another object, it has to logically reappear on the other side. But that critical debate is still going on. Is it simulation, or is it just highly sophisticated correlation? And the evidence for correlation is still there in the physically impossible hallucinations. It frequently generates transitions that just defy Newtonian physics, like glass shattering a few milliseconds before impact. It's a probabilistic rendering engine, not a true physics engine.
Okay, so if Sora is the passive video generator, DeepMind's Genie solved the problem of making these generative models interactive. Sora is incredible to watch, but you can't play it, which is the ultimate goal for an agent.
For robotics or gaming, you need a model that understands actions and allows for control. The huge challenge is that the vast pool of internet videos, YouTube and so on, it lacks explicit action labels. We don't know what button the gamer pressed between frame teller and frame town plus $1.
And Genie's answer to this was the latent action model, or LAM.
All right, Genie uses a sophisticated VQVAE approach to look at two sequential frames and, crucially, infer the discrete action. That must have caused transition between them. It's learning an inverse dynamics model. And then a subsequent dynamics model learns to predict the next frame, given the current frame, and that inferred action. This system turns static, unlabeled video into structured, actionable experience.
And the result is that Genie can take a single static image, like a screenshot from an old Mario game, and turn it into a playable 2D platformer. That's a massive breakthrough for training interactive AI on just ubiquitous, unlabeled data.
It completely solves the cold start problem for interactive agents. It bypasses the need for all that expensive human-labeled action data.
And finally, we see the inevitable convergence of these two schools of thought. The fast, planning-focused Dreamer RSSM and the high-fidelity diffusion generative models. This is what we can call Dreamer 4, or the Diamond's work.
This is the latest leap forward. The Dreamer lineage, while it was fast and efficient for planning, it always suffered from the blurry images that its VAE decoder produced. And this made interacting with small, subtle objects like the diamonds in Minecraft extremely difficult. So Dreamer 4 just replaced that blurry VAE decoder with a high-fidelity diffusion model decoder.
But wait, we just established that diffusion models are inherently slow. They take hundreds of milliseconds or even seconds. How can you integrate such a slow component into the inner loop of an agent that needs to plan dozens of steps ahead in real time?
That's the innovation in optimization. They didn't use a standard slow diffusion model. They optimized it specifically for speed and trajectory consistency using distillation techniques. And the benchmark success achieving a 0.7% success rate in Minecraft diamond retrieval from an offline dataset that validates that high-fidelity diffusion models can now be made computationally feasible. They can be optimized to be fast enough to contribute meaningfully to the internal planning architecture. The lines between the two schools are definitely blurring.
Everything we've talked about so far, car racing, Atari, Minecraft, it's all been in these contained, digital, and, largely deterministic environments. Now we have to talk about the monumental transition, moving world models into physical, embodied systems. Things like robotics and autonomous vehicles, where safety, sensor fidelity, and real-world unpredictability are absolutely paramount.
This transition, it changes the entire objective function of the world model. For a robot or an autonomous vehicle, an AV, you don't just need a coherent video. You need actionable sensor data, precise control, and you need safety validation for scenarios you've never even seen before. And this is where the autonomous driving sector became the first major proving ground.
Let's start with Wave and their large multimodal model, GAIA1. Their philosophy is AV 2.0, this idea of end-to-end learning where the car learns to drive like an expert human, bypassing millions of lines of hand-coded rules.
GAIA1 is a massive 9 billion parameter multimodal world model. Architecturally, it's an autoregressive transformer. Think of it like a GPT model, but applied to video prediction. It predicts future video based on inputs that include video, text prompts, and, critically, the ego vehicle actions. It predicts the future visual stream based on what it decides to do: brake, turn, accelerate.
So what's the strategic use case for a driving startup using GAA1? Why spend all these billions of parameters generating high-fidelity video if, as we'll see, a company like Wabi argues pixels aren't even enough?
Wave uses it to solve the infamous long-tail problem of autonomous driving data. Most of the data collected by AVs, 99% of it, is just boring, stable highway driving. The 1%, the rare, dangerous, or highly unpredictable edge cases, that's what causes accidents. And that's what requires billions of miles of testing. The world model generates that needed data.
Huh. So they use the world model to create synthetic training data? It's the ultimate dream sequence for the car.
Precisely. They can take a boring, real-world clip and just prompt GIIA1, generate a scenario where a child chases a ball into the street, or make the traffic light malfunction during a downpour. The model generates that imagined, dangerous scenario, and the driving agent can safely train on millions of near misses and bizarre edge cases without ever risking life or limb in the real world.
Okay, now let's look at Wabi World, which takes a philosophically different stance. They argue that generative video, just pixels, isn't enough because of the reality gap.
Right. Wabi, which is led by Raquel Urdison, argues that the most critical sensor data for a car LiDAR and radar, they see the world differently than a camera does. Predicting beautiful high-fidelity pixels is insufficient if the actual sensors the car relies on for distance and velocity are getting distorted or inaccurate data, so they argue you need to simulate the sensor data directly. Wabi World builds a reactive digital twin that focuses on high-fidelity sensor simulation.
And their training method is fascinating. It's called closed-loop adversarial training.
It's automated stress testing. They build their reactive simulator, the world model, and they pair it with a dedicated adversary AI. The adversary's only purpose is to create scenarios specifically designed to push the limits and make the driver AI fail. It's constantly exploiting weaknesses in the policy. And this continuous, automated red teaming allows the driver to learn from millions of novel, tricky edge cases safely inside the simulator, constantly improving its robustness.
That sounds like a much safer, more scalable way to close the reality gap for sensor-based perception. Their research has even applied world model concepts to 3D spatial data, right?
Yes, their Copilot 4D research used discrete diffusion techniques to predict future LiDAR point clouds. It confirms that these underlying architectural concepts developed in Dreamer modeling the world based on predicted state transitions are fully applicable to complex 3D spatial data, not just 2D video frames.
So we've talked about closing the reality gap with synthetic data at Wave and closing it with adversarial sensor simulation at Wabi. But the biggest challenge still remains. Can you really trust a policy that learned in a dream when you deploy it in the messy physical world?
And that's exactly what Google's Unisim is targeting. Unisim stands for Universal Simulator. Their key insight was that maybe the reality gap isn't fixed by just better simulation of a single domain, but by scaling the sheer breadth of data the world model learns from. The methodology was to train on this massive unification of highly diverse data sets: robotics manipulation data, internet navigation data, human manipulation videos, everything.
And by pooling the dynamics from every corner of the digital world, what was the surprising outcome for physical robotics?
It suggested that the difference between simulated physics and real physics, it becomes negligible for control tasks if you scale the model sufficiently to understand all the underlying dynamics. And the proof was in the deployment. A robot policy trained entirely inside the Unisim hallucination learning complex, multi-step tasks like washing dishes or opening specific drawers could be deployed to a physical robot, and it would work zero-shot.
Zero-shot performance. So no retraining in the physical world was required at all.
None. The simulation was so complex and so accurate that the physics just became largely irrelevant for the control purposes. And this fundamentally challenges the necessity of painstaking, slow, real-world data collection. It proves that the code for the next generation of robots can, in fact, be dreamt.
The shift from engineering control systems to engineering the simulation itself is truly tectonic, but the world model concept is going far beyond vehicles and robotics. Where else are we seeing this architectural shift being applied?
Anywhere there are dynamic systems with complex causal rules. Take biology, for example. A company called Noetic is building Octo, which is a transformer-based world model of human biology. Instead of predicting the next video frame, Octo predicts the next transcriptomic state of a cell, so its gene expression, after being treated with a specific drug or compound.
That's the ultimate in silico clinical trial. You're modeling how a biological system reacts to an intervention entirely in the latent space.
That is the goal. And similarly, in climate science, models like NVIDIA Earth-2 and the Walia World of Weather project are creating climate world models. These couple AI models of the atmosphere, the ocean, and land dynamics. And because they operate in the latent space, they can run thousands of complex climate simulations, predicting weather patterns or climate outcomes at a fraction of the cost and speed of traditional supercomputer physical models. It lets researchers test interventions so much faster.
This has been an incredibly detailed trace of the evolution, from those modular VAE RNNs in 2018 to the massive generative models of today. To help everyone synthesize the strategic landscape, let's just summarize the three dominant architectural paths we've covered and their inherent trade-offs.
Yeah, we've seen three pretty clear strategic paths emerge, and each one is optimized for different needs. It really reflects a core engineering choice between speed and fidelity. First, you've got the RSSM Dreamer lineage. This uses discrete or categorical latents, which prioritize stable, causal encoding. Its main strength is fast inference speed, typically under 10 milliseconds. This makes it the gold standard for real-time control for planning and for core reinforcement learning tasks where you need rapid, high-frequency decision-making.
Okay, second, the JEPA architecture from Meta, representing that representation-only school of thought.
JEPA uses abstract continuous latents, and it's built for sheer speed and noise resilience. It boasts very fast inference because it completely avoids the complex step of pixel reconstruction. It's best suited for representation learning, classification, and high-speed planning, where the semantic state is much more important than the visual texture.
And finally, the large-scale diffusion world models like Sorta and Diamonds, which are all about maximum fidelity.
Right. These use continuous patches or 3D tokens. They deliver the highest visual fidelity and the best implicit physics understanding. But they have one massive, crucial drawback: very slow inference speed, often over 100 milliseconds, and sometimes stretching into seconds. They're best used for high-fidelity offline simulation, synthetic data generation, and applications where latency is less critical than visual realism.
That speed difference, 10 milliseconds for a robot versus 100 milliseconds or more for a high-fidelity generative model, that brings us directly to the single biggest engineering bottleneck right now: inference speed and latency.
It is the ultimate hurdle for deploying these cutting-edge diffusion world models in production robotics. A physical robot has to operate at 100 Hz. That means it needs a decision every 10 milliseconds. A standard high-fidelity diffusion model needs 20 to 50 denoising steps to generate a clean output, and that's what pushes the latency into that second-long range. They're just too slow to be used in the inner planning loop of any autonomous system that needs to react quickly.
So if the diffusion approach gives you the best implicit understanding of physics, but it's too slow to use, what are engineers doing right now to bridge that 90 millisecond gap?
They're using distillation techniques. This is a massive area of focus. The main strategy involves consistency distillation and creating latent consistency models, or LCMs. And these methods are used to train a smaller, faster student model to mimic the outputs of the massive, slow, multi-step teacher model.
And the result of that distillation is a much faster model.
It allows researchers to distill the models down from 50 steps to just 1 to 4 steps. Now, this might sacrifice a tiny bit of generative fidelity, maybe a texture slightly off, but it makes them fast enough. It makes them viable for real-time control, which is what we saw with the success in Dreamer 4. They're choosing speed over perfection.
Once that latency issue is solved, where do researchers go next? What's the conceptual frontier beyond just generating a sequence of future frames?
The next major frontier seems to be the Generative World Explorer, or GenX, framework. And this focuses on imaginative exploration and belief updating.
That sounds like a cognitive extension, like giving the agent the ability to pause and muse on its situation.
Exactly. The core concept is that the agent can imaginatively explore its environment before it physically moves. So if a robot encounters a closed door, GenX will generate a distribution of possible future videos of what might be behind that door based on its internal world model. A hallway, a staircase, a closet, each with a probability attached.
And the practical implication of this internal dream exploration, what's the point?
It's used for belief revision. The agent uses that imagined observation, the dream, to update its internal belief state and formulate a better, risk-reduced plan. And it does all of this without expending physical energy or taking unnecessary risks. It's the highest form of the AI equivalent of looking before you leap. It minimizes the cost of uncertainty.
So finally, let's talk strategic opportunity. We've profiled Google, Meta, OpenAI. They're all building these enormous foundational models. If a founder is listening right now and sees the power of this tech, how do they enter the market without competing directly against the hyperscalers?
The foundational models, the Soras and the Unisims, they're pretty much locked down by the giants. The opportunity lies entirely in vertical world models, building a highly specialized model for a specific high-value niche domain where data is scarce or expensive and proprietary knowledge is key.
And where could that kind of specialization really pay off right now?
Well, think about highly controlled, sensitive environments. Industrial digital twins are a perfect example. A world model that's specifically trained on one factory floor, its specialized machinery, its proprietary throughput dynamics, its failure modes. It can simulate the effects of layout changes or supply chain disruptions in its dream space before managers ever have to move a single piece of heavy machinery. Another one is surgical simulators, which can model human tissue and bone dynamics with realistic physics feedback, allowing surgeons to practice complex, high-stakes procedures that are impossible to simulate with generic game engines. These leverage the core competence of the world model causal prediction to create massive value in specific high-stakes domains. #outro.
This evolution is just remarkable. We started this deep dive talking about systems that could only recall patterns based on historical data. We've moved decisively to systems that understand the dynamics, the internal mechanisms, and the causality of their environments. The promise is clear. The code for the next industrial revolution will be dreamt, not written.
It fundamentally changes the relationship between AI and reality. We're witnessing the construction of robust, artificial realities, simulations that are stable enough to serve as the ground truth for complex policy and sophisticated long-horizon planning.
So what does this all mean for you, the listener? What's the provocative thoughts to take away from this journey into simulation?
Consider this. The ultimate, unspoken goal of this entire field is the creation of what researchers call the Turing test for reality. That is, creating a simulation, a world model that is so accurate, so comprehensive, that an agent trained entirely within it cannot distinguish it from the physical world. If Unisim can already teach a robot zero-shot dishwashing, how far away are we from a simulation that is functionally indistinguishable from our own reality for control purposes? That horizon, the point where the distinction between simulated and real just breaks down for an intelligent system. That's the end game, and we are rapidly approaching it with these new architectures.